Welcome to the next episode of Rolling Physics.
Today we're learning about the Doppler effect.
I'm the Doppler Effect.
This is the Doppler Effect, y'all.
So the Doppler effect is all about the shift in the wave that occurs as the source of the sound or the light is moving. The faster it's moving towards you, the louder or the brighter the light will, or the sound will appear.
Hi, I'm Plain Old Robert, and this is the equation of the Doppler effect. Now let's go over each of these symbols one by one for all you Physics 1 students and Tyler.
This is backwards Andy, and he represents frequency detected, which is a frequency that would be heard or detected by an observer or scanner. Say hi backwards Andy. This is badge of the bone Robert, and he's holding up the symbol for frequency of the source. Here our friend Evan is holding up the symbol for velocity of the observer. And here our grandma Nathana is holding up the symbol for velocity of the source.
This is V.
This is V.
This is V.
The symbol for the velocity
That's
of
V.
sound,
That's V.
which is equal to 343
For sure it's V.
meters per second.
This is V.
V.
I'm the Doppler Effect.
Here we have our friend the Doppler effect, showing us how the frequency detected is equal to the frequency of the source times velocity minus velocity detected over velocity minus velocity of the source.
Let's see the Doppler Effect in action.
Let's use this example to calculate the change of frequency based on the Doppler effect.
I'm the Doppler Effect.
First, let's give values to our variables.
So, the velocity of the Jeep was approximately 25 miles per hour. So, converting that to meters per second, it was approximately 11.18 meters per second. The velocity of the source was 11.18 meters per second. The velocity of sound can be used as being 343 meters per second. And the velocity of the detector was 0 meters per second because the observers did not move as the Jeep went by.
Oh, hi. Didn't see you there. What are we on? Hertz. That's right. The average Jeep's horn emits a frequency of 500 hertz. So for the frequency of this source, we're going to use 500 hertz.
Now let's calculate the frequency of the horn when the Jeep is traveling towards the observer.
So after plugging those values into the equation, we get frequency at detector or observer equals 500 hertz times the quantity 343 meters per second minus 0 meters per second over 343 meters per second minus 11.18 meters per second as shown by this paper, which gives us that frequency of the detector equals 516.85 hertz. So now we calculated the frequency detected of the Jeep horn as it traveled towards the observers. Now, let's calculate the frequency of the Jeep horn detected as it travels away from the observers.
Oh hey! As you can see, the velocity of the source is now negative because the Jeep was traveling away from this observer.
Obviously, the Jeep's horn remained the same, so the frequency of the source stayed at 500 hertz.
You can do some 8th grade
Let's plug
things,
these values into the equation.
After plugging those values into the Doppler effect equation, we get frequency of the detector equals 500 hertz times 343 meters per second minus 0 meters per second over 343 meters per second minus negative 11.18 meters per second. And the answer is 484.22 hertz, as our friend Robert is showing us. As you can see, the frequency detected while the Jeep is traveling towards the observer is greater than the frequency of the source, or the actual frequency of the Jeep horn, while the frequency detected of the Jeep traveling away from the observer is less than the 500 hertz of the initial frequency of the source.
Thank you for watching this episode of Rolling Physics.
Baby, I should cry.